I'm William Collins from the University of Kansas. I'll be moderating today. We have two really good speakers, Dominique Coletti and Dennis Golobec. So first up we have Dominique Coletti. He's a principal professional associate in Raleigh, North Carolina with HDR, and he has 28 years of structural design experience. He's authored and presented numerous papers on bridge design and is a member or chair of technical committees of several national professional organizations. Today he's going to be talking about practical implementation of stability bracing, strength, and stiffness guidelines for steel girder bridges. Please join me in welcoming Dominique.
Thank you, William. I always appreciate it when the moderator sets up the slides for me so that I don't embarrass myself with my technical incompetence. Good afternoon, everyone. As William mentioned, the topic of my presentation today is a bit of a mouthful. Practical implementation of stability bracing, strength and stiffness requirements for steel girder bridges. That's a lot of words, and it sounds scary, but it's really not. I hope through the course of this presentation you'll see that the topic we're going to talk about today is much, much less intimidating than the title of the presentation. Before we start, I do want to take a moment to acknowledge my co-author, Mike Grubb, of M.A. Grubb and Associates. I've given this presentation a couple of other times. Mike's not here today. He's been there once before, and the other time he was not. None of those other times did he ever answer any of the questions afterwards. So today, if you have a question, you need to write it down and give it to him. I'm going to email it to Mike, and we'll get an answer back to you in an hour or two. The organization of the presentation today is fairly straightforward. We're going to begin by talking about the stability bracing, strength, and stiffness requirements for steel girder bridges. We'll talk next about how to implement them in a practical AASHTO LRFD bridge design. Then we'll walk through a short design example and wrap things up with a quick summary. So let's go ahead and get started talking about the stability bracing requirements for steel girder bridges. Now, a typical steel girder bridge has many components, and the three that are probably of the most interest when we're talking about stability bracing are the deck, the girders, and the cross frames or diaphragms themselves. And that term stability bracing refers to any bracing that helps to resist lateral torsional buckling of the girders. Now, if you're in a positive moment region and your deck is in place and hardened, that composite concrete deck serves to continuously brace the girders. But if you're in that positive moment region before the deck is hardened, or if you're in a negative moment region, the girders are braced at discrete points, brace points, and they're braced by the cross frames or diaphragms. And the cross frame spacing represents the unbraced length of the girder. Now, these are familiar concepts. All bridge engineers know about this, and you deal with it all the time. In fact, it's a common design exercise to balance cross frame spacing versus girder size. So you're familiar with this stuff. You know how to do it, but there may be a question in the back of your mind, like, okay, but how strong or how stiff does that cross frame need to be in order to function to adequately brace the girder against lateral torsional buckling? Now, traditionally, when we've been designing cross frames or diaphragms, those designs have gone down one of two broad paths, depending upon the nature of the structure and how complex it is. If you have a more complex structure, maybe a curved or severely skewed steel girder bridge, you probably have a refined analysis. In the old days, maybe you had a V-load analysis. Today, you probably have a 2D grid or a plate and eccentric beam model, or maybe a 3D finite element model. And that refined analysis is going to give you a lot of analysis results, including a full set of force results for the cross frames, including the dead loads and the live load forces in those cross frame members. And those dead load and live load forces in the cross frames or diaphragms are going to be fairly significant, and the resulting cross frame designs are going to be fairly robust, and by inspection, they have sufficient strength and stiffness to function to brace the girders. On the other hand, if you have a fairly simple bridge, maybe a straight bridge with little or no skew, you're probably designing it using a line girder analysis. And as you know, a line girder analysis only considers the girder itself. It doesn't really evaluate the interaction of that girder with the rest of the structural steel framing system. So that line girder analysis isn't going to give you any cross frame results. And that's okay. Typically in these simpler structures, the dead load and live load forces in the cross frames are fairly small and can be neglected. And that's why AASHTO doesn't require you to use a refined analysis for these simpler bridges in the first place. Instead, you can move on and you can design those cross frames for wind loads and considering the maximum slenderness limits for the individual cross frame members. Now that changed with the development of stability bracing strength and stiffness requirements. These requirements were developed by Dr. Joseph Ura at the University of Texas at Austin, and they were published in the AISC Engineering Journal back in 2001. They were eventually adopted by AISC in their specifications for structural steel buildings, where they appear in Appendix 6.3. Later on, they also appeared in the FHWA Steel Bridge Design Handbook, where they show up in Volume 13, Bracing System Design. They first appeared there in the November 2012 publication of that manual. It's since been updated right around the end of last year. Now, there are two primary design requirements. The first is that cross-frame or diaphragm has to have sufficient stiffness to help resist lateral torsional deflections of the girders. You can see it's a fairly simple equation that we're looking at. It has consideration of the span length L, the girder's factor design moment M sub F, the number of braces N, the girder stiffness EI, and the moment gradient C sub B. The second requirement is that cross-frame or diaphragm has to have sufficient strength so that the cross-frame can resist the forces that are applied to it as it resists the tendency of the girder towards lateral torsional buckling. Again, it's a fairly simple equation. It has all the same variables as the stiffness requirements equation, only now there's also consideration of the unbraced length, L sub B, and the girder depth, H sub 0. Now, these are fairly simple equations. All the variables are very familiar to you as bridge engineers, and you can look at them and say, I can calculate all those variables, and I can run these equations. It's no problem. But you're still left with the question of how do I specifically implement these equations in an AASHTO LRFD bridge design? Well, that's what we're going to talk about next. As I mentioned earlier, these equations, all these provisions appear in the FHWA Steel Bridge Design Handbook, and it's a very nice presentation that they have in there. All the equations are presented, all the variables are defined, there's figures and there's discussion, and you can read through all of this, and eventually in the discussion you'll get to a point where it says, using these equations, the stability bracing forces are additive to the bracing forces resulting from a first-order type of analysis, dead load, live load, etc. Now, unfortunately, the discussion stops at that point, so you're left with a few questions. Okay, but I'm doing a line girder analysis. I have a simple bridge. I don't have cross-frame forces from my analysis results, so I don't have those other dead load and live load forces. Is that okay? Do I need to calculate them somehow? Are there other loads that I need to consider? And since I'm doing an AASHTO LRFD bridge design, I need to know what limit states I need to investigate. And then I need to know what load factors and load combinations are associated with those limit states. You might also say, hey, I've read through all this material, it looks really good, but they only talk about simple spans and positive moment regions. I have a multi-span continuous bridge. What do I do in the negative moment region? We're going to try to answer some of those questions today, and we'll walk through them one by one, beginning with a discussion of some of the applicable loads. So, for example, you're designing a simpler bridge, maybe a straight bridge with little or no skew, one that looks like the bridge in the photo on this slide. You're probably doing a line girder analysis. And as we mentioned earlier, that line girder analysis is not going to give you any cross-frame forces, and that's okay. As we said earlier, those dead load and live load forces in the cross-frames or diaphragms for a simple bridge like this are typically negligible. You can go ahead and move on and just calculate the wind loads next. And the wind loads are typically calculated for these simpler bridges using simple methods. Most designers will make some simplifying assumptions, and they'll use some hand calculations to come up with the wind loads in the individual cross-frame members. And then obviously you can calculate the stability bracing forces using Dr. Ura's equations. Now, with regard to limit states and load combinations and load factors, you can find those by looking back at the AASHTO LRFD bridge design specifications and applying some engineering judgment. The table that's presented on the slide here was developed over the course of several projects that came through our office, and that's exactly what we did. We looked back at the AASHTO LRFD bridge design specifications, at the load combination and load factors that are in Chapter 3. We applied a little bit of engineering judgment in developing some construction load cases. We had a couple of discussions with the original researchers who put all this material together. What I really want you to think about, though, when you're looking at this is that these load combinations are used to calculate the factored girder design moment. That factored girder design moment is one of those key variables that goes into Dr. Ura's equations. And what I want you to remember is that once you run those equations using the factored girder design moment, The results that you get out of those equations don't need to be further factored for combination with other load effects. A couple of other things to keep in mind about these tables, and they're mostly associated with the fact that some of the load combinations in that table on the previous slide were for construction cases. Whenever you're looking at a construction case, some reasonable engineering judgment needs to be applied. For example, if you think about it, a contractor isn't going to be out casting a deck for a bridge in the middle of a windstorm. Only makes sense. Consequently, you shouldn't be applying the maximum factored construction dead loads and live loads in the same combination with the maximum factored wind load effects because they don't occur simultaneously. Now, a lot of states are beginning to develop some very specific and good guidelines for what they want to see addressed in construction load cases. They're specifying the loads, the load combinations, and the load factors that they want you to investigate. Now, if you're working for an owner agency that has those kind of guidelines in place, obviously you should follow those guidelines. But if you happen to be working for an owner agency that doesn't provide those guidelines, that's okay. You can develop your own, similar to what you saw on that previous slide. Now, if you're designing a multi-span continuous bridge, when you're in the positive moment region, things are going to be fairly easy. All of Dr. Ura's equations and provisions are going to be able to, you're going to be able to directly apply them in those cases. But when you get to the negative moment region, you're going to have some questions. Dr. Ura's original research focused only on simple span structures, so he only looked at positive moment regions. He wasn't able to provide any guidance for negative moment regions and how to deal with them. So you're going to be left with a few questions. First of all, you may ask yourself, well, what about the deck? Does the deck serve to function to stabilize those girders in the negative moment region? Dr. Ura's research didn't address that, so for now, the conservative answer is to assume that it does not. But on the other hand, you don't want to be too conservative, so when you're identifying that factored girder design moment that goes into the equations, it's too conservative to use the maximum negative moment that occurs directly over the pier. Instead, it's probably more reasonable to assume that the bearings and the anchor bolts provide restraint for the girders right at the pier. And you go out to the first cross-frame line and you can choose, you can identify the factored girder design moment at that location instead. Also, as you go from the positive moment region to the negative moment region on your bridge, if there's significant changes in the cross-frame spacing or the girder section properties, you want to be using everything consistently. Choose and investigate the stability bracing effects for the positive moment region using the cross-frame spacing and girder properties for the positive moment region, and similarly for the negative moment region. Okay, in addition to these interpretations that we just talked about, there are also some simplifications that you can apply to help streamline some of your calculations. And these are all related to the three beta factors that comprise the resistance side of these stability bracing equations. And the first one of these is the cross-frame system stiffness parameter beta sub b. Now, the equations for beta sub b that are presented in most of the research and in the FHWA Steel Bridge Design Handbook are conservatively based on a case of only 2 girders. Now, most bridge designs have 4, 5, or more girders, so calculating beta sub b using equations based on 2 girders is conservative, but not excessively so, and it's fairly easy to implement because the equations are all there. Now, if for some reason greater refinement is desired, that's okay. You can read a little bit further on in the Steel Bridge Design Handbook. You'll get to the section that discusses lean-on bracing, and it provides some discussion and an equation in there that helps you consider the effect of additional girders in the cross-section. Next is the Webb distortional stiffness parameter beta sub sec. Again, there's equations right there in the FHWA Steel Bridge Design Handbook that you can apply very easily. But for most cases, in a practical bridge design, you probably have a full-depth cross-frame. And if you have a full-depth cross-frame, those Webb distortional effects are probably going to be fairly negligible. And instead, you can take that beta sub sec term as infinity. You do need to keep in mind that AASHTO allows you to use shallower cross-frames or diaphragms. For example, if you're designing a rolled beam, AASHTO allows you to have your cross-frame or diaphragm be as shallow as half the depth of the girder. Now, in those cases where you have a shallower cross-frame or diaphragm, it may be prudent to more explicitly investigate the beta sub sec term. Again, it's easy to do. The equations are all there. You just need to walk through them as you go through the height of the girder. You'll have a region where perhaps only the Webb is effective in resisting that Webb distortional effect, You'll have another region where the web and a stiffener may be effective, and you may have yet a third region where a web, the stiffener, and the crossframe or diaphragm are all effective. You run the equations for each one of those regions, sum them up to get the overall term. Finally, there's the in-plane girder stiffness parameter, beta sub g. Now, the equations for beta sub g were developed assuming only one brace at mid-span. This is a conservative worst-case simplification when more than one brace is provided, as is typical for most bridges. Theoretically, you can derive equations that will address cases with multiple braces, but for most bridges that have 4, 5, or more girders in their cross-section, the effect of the beta sub g term is less significant. Now, if you have a narrower bridge and you find that that beta sub g term is beginning to dominate your calculations of the overall bracing stiffness, you may want to step back and take another look at that bridge, because global system buckling may be a concern. And at that point, it may be prudent to do a more refined analysis. And I don't necessarily mean just a more refined analysis of the stability bracing requirements. I'm talking a little bit bigger picture, a more refined analysis of your overall superstructure system, a global system buckling analysis. Okay, over the course of the past few slides, we talked about some interpretations and simplifications, and I hope you see that most of what we talked about was geared towards something practical, something making things a little bit simpler, and we weren't afraid to include a little bit of conservatism as we went through the process. When we walk through the design example next, I hope you'll be able to see that adding that conservatism isn't necessarily a bad thing, and it's not going to beef up your crossframe design unnecessarily or excessively. So this design example we're going to walk through today comes from a practical design project that came through our office recently and involved the design of 3 straight steel I-girder bridges as part of a multi-level interchange. These are fairly simple structures, straight with little or no skew, and as you look through the basic design parameters, you're going to see there's nothing too special about these bridges. The span lengths, the girder spacing, the web depths, the crossframe spacing, all these various parameters are fairly routine looking. So we went ahead and ran through Dr. Ura's equations, just as they come right out of all the published material. We investigated the required crossframe stiffness and the required crossframe strength, just using the same equations we've been talking about throughout this presentation. I want to give you a feel for some of the numbers that are in here, so we're going to walk through a couple of representative design values. The span length for the particular case that we're going to talk about today was 147.5 feet, about 1,770 inches. The effective moment of inertia of the girders was 981 inches to the fourth. The unbraced length, that's the cross-frame spacing, was 24 foot 9 inches, 297 inches. And the girder depth, measured as the distance between the flange centroids, was about 69 inches. Now you may notice that most of these variables are listed up here in terms of inches. Those of you in the room who are millennials may be thinking, I bet they programmed all that in the MathCAD worksheet. And you'd be right. That's exactly what we did. And the reason why I wanted to mention that was to emphasize again, these equations are really simple. It's very easy to program them in an Excel spreadsheet or a MathCAD worksheet. Okay, we went through and we calculated the actual crossframe stiffness that was being provided by the crossframe design that we were proposing. And as you look through these variables here, you can see that the crossframe system stiffness parameter for this particular crossframe was 1.5 million kip inches per radian. The web distortional stiffness parameter was 12.9 million kip inches per radian. And the in-plane girder stiffness, beta sub g, was 340,000 kip inches per radian. Now, I don't want you to worry too much about the individual values of all those terms, but I do want you to look at the relative magnitude of them in comparison to each other. Look at the web distortional stiffness parameter, 12.9 million kip inches per radian. It's nearly 10 times higher than the next higher value. As you're going to see in a few slides, we're designing a full-depth crossframe here. And as I mentioned earlier, when you have a full-depth crossframe, those web distortional effects are practically negligible. We probably could have much more easily just taken this value as infinity, and it probably wouldn't have really affected the final design results all that much. Okay, you take these 3 terms, and to add them all up, you're going to go ahead and take the inverse of the sum of the flexibilities represented by all these stiffness terms. And that's shown in the equation near the top of the screen. If you walk through all of the math, you find that the overall actual crossframe stiffness is 272,000 kip inches per radian. Next, we calculated the required crossframe stiffness. Now, in this particular case, we were investigating the negative moment region, and we were looking at the final conditions for the bridge. So the deck is in place, and we're looking at a case where live load can be applied. So we walked through the typical AASHTO, LRFD strength limit states. We found that the strength 1 limit state was the controlling case for the factored girder design moment, and that factored girder design moment was 77,000 kip inches. We plugged that into Dr. Ura's equations, and we were able to calculate that the required cross-frame stiffness was 225,000 kip inches per radian. And if you remember back from the previous slide, the provided cross-frame stiffness, the actual cross-frame stiffness, was 272,000 kip inches per radian. Since our provided value was greater than our required value, we've demonstrated with these calculations that the cross-frame that we're proposing has sufficient stiffness to function adequately as a brace for these girders. After that, we investigated the cross-frame strength requirements. Again, we just used Dr. Ura's equations. We calculated the required strength using equation number 3, shown on this slide. And that equation gives you a required cross-frame strength represented as a moment value. It's a moment demand on the cross-frame. You can take that moment and break it into individual components, a top chord force, a bottom chord force, and a diagonal force. And you can do this using very simple equations that Dr. Ura provides in his work. In fact, they were presented back earlier in this presentation. Once we've got those stability bracing forces, we can go and calculate the wind load forces in those cross-frame members. Again, just using some simplifying assumptions and hand calculations. We appropriately factor them for each one of the load cases that we're looking at, and we add them all together. You can see the results in the table at the bottom of this slide. Now, obviously, as you'd expect, if you include consideration of the stability bracing forces, your design loads are going to be higher than if you only considered the wind loads. That just kind of makes sense. You're adding two numbers together. What I really want you to notice is that those final design values, those final forces, they're not really all that high. And you can see that played out in the final cross-frame design that's presented here. It's a fairly reasonable looking cross-frame. The member sizes are all fairly reasonable. The top chord, the bottom chord, and the diagonals are all 5 by 5 by 7/16 inch angles. It's a fairly routine looking cross-frame. Now, keep in mind that's only one design example. It wasn't the result of any kind of comprehensive study, so don't take those numbers too far out of context. But I really don't have any reason to believe that the results would be fundamentally different for other similar types of bridges. Okay, with that, we're going to take a couple of minutes here to wrap things up. Today, we talked about the stability bracing, strength, and stiffness requirements for steel I-girder bridges, and we talked a little bit about how you might implement them in a practical AASHTO LRFD bridge design. Now, I hope you'll agree after seeing these equations that Dr. Ura's equations are fairly simple and fairly easy to use, but they do require a little bit of interpretation if you're going to use them in a bridge design. And we talked about that today. We talked about appropriate limit states, load combinations, and load factors. We talked about how you might consider these effects in the negative moment region. And we also talked about some practical design simplifications that you might use to help streamline your calcs a little bit. We also walked through a simple design example, the main point of which was to show you that the forces that you calculate using these equations are really not all that excessive, and the resulting cross-frame member sizes are really fairly reasonable. Finally, I do want to take one moment to make a final thought, and I'd like to emphasize the value of investigating the strength and stiffness requirements for stability bracing. There have been several recent cases of problems being experienced during construction of steel I-girder bridges, and these problems have been traced back to problems with the bracing, and they point to the need to carefully consider the design and behavior of cross-frames and diaphragms in steel I-girder bridges. These stability bracing, strength, and stiffness provisions that we discussed today are a valuable and important part of your overall design process. And with that, I think we have a few minutes for some questions. I do have the PDH code up here. William wanted me to remember to point that out to everybody. I love going right after lunch. Nobody asks any questions.
We have time for a few questions.
All right, thank you very much.
That was great. Thank you, Dominique. So I'll go ahead and put the codes back up here. So PDH code 24421. So our next speaker is Dennis Golubeck. Mr. Golubeck recently joined Kissinger Campo and Associates, where he's the chief structures engineer. He was previously at the Florida DOT as an assistant state structures design engineer. Mr. Golubeck had 21 years of experience in bridge design with a particular emphasis on steel plate girders with skewed and or curved geometry. And today he's going to be talking about Florida DOT's criteria for wind on partially constructed bridges. Please welcome Mr. Golubeck.
Okay, thank you. Turn this one on. So what we're going to talk about now is basically about estimating the wind loads during construction, and specifically about I-shaped girders when they're up on the substructure supports, but they do not have any deck in place. And so before I begin, I just want to make some acknowledgements here. Christina Freeman, who I worked with FDOT, she's with FDOT. She was the co-author, and she's here in the audience. Dr. Consalzio and Gurley from the University of Florida, they were the principal investigators for the research project. And they had subcontract the actual wind tunnel testing from the Western Ontario, University of Western Ontario, and that was Kong was the authors of that aspect of the research project. And so let's just go back a little history here and talk about what we've had done in the past. And if you've been doing bridges in Florida for a while, you might remember back in 2000 was the first time they started requiring the engineers to check for stability during construction for wind. And basically the rule was use 50% of the final design loads in the bridge. So basically you were using like the same drag coefficients between the final structure and the partially completed structure. And then in 2007, with AASHTO LRFD 3.4.2, they started specifying the load combination for constructability. So Florida followed that. 2009, they made a major switch, and they went to the ASCE 7 method, and that uses the 3-second gust. Remember, AASHTO was based on the fastest mile, so that was a major change in the philosophy of wind pressure. And then 2015, which is the recent thing, which is this presentation's about, they did wind tunnel tests and they came up with new pressure coefficients for different shapes of girders. And recently, AASHTO LRFD in the 2016 interims, they now adopted the 3-second gust too, and the fastest mile is no longer there. So what are we talking about? You know, we have some I-shaped girders up there on the substructures. They're at a certain spacing. They're at a certain depth. Wind is blown across this system. How are we going to estimate the wind loads on this system? What are the wind loads per girder? How much wind loads do we have? And so just to get our minds thinking, I wrote up some true and false statements up here. I'm not going to ask for answers now, but you might want to just think of what your answers would be. So true or false? Only the windward and leeward girders receive wind loads. Is that true or false? The drag coefficients are equal for all beam types. True or false? The wind velocities are the same for the continental USA. True or false? The drag coefficients for the completed bridge are the same for the partially constructed bridge. True or false? The girder spacing does not affect the wind load. And finally, the FDOT wind loading criteria reasonably estimates the wind pressure on each girder. So I'm going to go through the presentation now. Keep those things in mind, and at the end, we'll go through these true and false statements again. And so let's talk about the main factors for the wind pressure. Here's the equation. This was out of ASCE 7. Now AASHTO has adopted it. You can see that it's 4 variables. Basically, you have a constant in the beginning, which is the air density. Kz is the velocity pressure exposure coefficient. V is the wind speed, which is squared. G is the gust factor, which for Florida we use 0.85. And Cp is the pressure coefficient and drag coefficient. I use the 2 words interchangeably. Sometimes you'll see drag coefficients, other times you'll see pressure coefficients. But what's implied in the Cp value is the shielding model, meaning how much is the wind being shielded from the windward girder to the other girders. So the 2 things we're mainly going to talk about briefly is about the wind speed, but then we're going to concentrate on the pressure coefficient and shielding model. So here's the wind speed. This is a map up here on your left. It's from the ASCE 7. This is what AASHTO just adopted in 2016. And you can see for most of the continental USA, it's 115. It's constant. But as you get to the coastlines, you see the contours start picking up, and specifically in Florida, we have several contours. So the FDOT is right now looking at a draft version. Instead of making the designers use all these different contours, maybe use only 4 of them. Let's look at all the counties, let's look at our districts, and try to make some consistency out of here, so we don't have one bridge for this and one bridge for that. That's still the draft, still being worked on. So here are the results. I'm going to present the results first from the wind tunnel tests. And there's the chart right there. And you can see the component type. So per I-shaped girder, steel, and a concrete girder, you see 2 different pressure coefficients, the 2.2 and the 2. And for a U-shaped girder, it's even another value, 2.2, and a flat slab's 1.5. But the major other division is the spacing to depth ratio. If you have a spacing to depth ratio less than 3, you have one shielding model, and a spacing to depth ratio greater than 3, another one. So what's the difference? So let's look at the spacing to depth ratio less than 3. Basically, that's maybe the traditional approach you have seen before. You take the projected height of the superstructure. So if you had it less than 3, you take the Cp of 2.2, you go through that equation, you get the wind pressure, and you multiply that by the projected height. That's the total wind load on that system for girders if you have anywhere from 1 to 5 girders. If you have 6 girders, 7 girders, 8 girders, you actually have to add another component of the wind to those specific girders with the other Cp value of 1.1. So how does that differ from the S/D ratio greater than 3? Well, we found out that that matters on the shielding model. And the shielding model for that is shown in that diagram where you see a Cp value of 2. So you calculate your pressure, multiply it by your depth of girder, but then you have to put pressure on girders 3, 4, 5, and so on with about 50% of the pressure coefficient. And that would be the total wind loading on your system. So you might be asking, well, how did we come up with that? You know, what's the difference? And before we talk about that, I just wanted to show you a slide on the wind tunnel test and just explain what happened. So we tested 1 girder, 2 girder, 5 girder, 10 girder systems. We tested several shapes of girders, steel I shapes, Florida I beams, a box shape. We tested at different cross slopes. We tested at different wing angles. The wind angle from the horizontal from 5 degrees down to 5 degrees up. So we ran all these tests. And just to note, when they actually did the testing, they could only measure 1 girder at a time. So for one set of criteria of cross spacing, wind angle, girder type, they had to run that test 5 times for the 5 girder system. And that's what you see in the little diagram there with the girder in red is the girder being actually measured, but they have to move all the other girders around to put it in its correct position. So here are the results. And this is for the Florida I-beams. And what you see on the x-axis is the girder position, and on the y-axis is the drag coefficient. And this is for all the tests for the Florida I-beams. This is for the single girder, 2 girders, 5 girders, and 10 girder tests. And you can see that girder 1, which is the windward girder, always had the highest pressure coefficient. It always received the most load. Girder 2, surprisingly, was mostly a suction, a negative wind load on it. Sometimes it was positive. Girder 3 had a lot of variability. It was either negative or positive. And then 4, a little less variability. And then it kind of got a little constant where girders past that were about 50% of the windward girder. So we go, okay, how can we make this a practical application for engineers? And we said, okay, here's an example. Here's a CP value for a specific test. And you can see each girder has its own pressure coefficient. And for each test, we have all those numbers tabulated. And you can see we said, all right, let's look at the projected height. If we add up all those pressure coefficients times the girder height divided by the projected height, can we get a reasonable pressure coefficient, and is it basically consistent? And we tried that, and we could not get it to work. And we go, okay, well, that's not working. Let's start looking at something else. So we go, okay, well, let's zero in on the 3rd girder. Remember how much variability there was in that 3rd girder? So we said, let's chart the drag coefficients, which is on the x-axis, and the spacing to depth ratio, which is on the y-axis. And what's very interesting, you can see that, anything less than 3, that 3rd girder was basically getting negative wind. But you go above a space into depth ratio, you got a positive wind. And so that's how we develop that S over D. When the S over D is less than 3, basically girders 2, 3, and 4 are not picking up much wind. You can use the projected height. If that S over D ratio is greater than 3, there's a lot less shielding going on. So now I want to change the focus from the wind loading criteria to how is that applied to steel bridge construction here. And as you know, in Article 3.4.2 is about the load factors for construction. And they tell you to check all the limit states, of course, but there's actually only 3 limit states we really worry about, and that's the strength 1, the strength 3, which has the wind in it, and the newer equation, which is for the fully erected steel work, is the 1.4 dead load and the 1.4 construction loads. But if you notice in the strength 3, I have the load factor highlighted because that's what it is pre-2016. Now in the 26 interims, AASHTO did not define what the load factor is. They're leading it up to the owner. And this is the new wordage in the 3.42 that it says that it has to be specified by the owner. And then if you go through Article Section 6, which is steel, 651 talks about you got to check for each stage of construction. 6741 tells you have to check the stability of the top flange before the deck hardens. 610.3 is all about constructability and how you design a discretely braced flange. That's all good. We have to have the wind loads for that. But there's also another reason we want to estimate the wind loads, and that's for the restraints on the substructure, for any temporary restraints before you place the anchor bolts, or if you're on false work, you have to give the loads to the specialty engineer so they can design the false work. So here's a quick video. I thought it was pretty interesting. And this is the Blanner-Hassett Bridge over the Ohio River. There you go. And you can kind of hear the wind in the background. These are about 300, 400-foot spans. And you can start seeing the cantilevers. Look at the cantilevers first. They're going to start swaying back and forth. And later on they say, oh, it's about a 50 mile per hour wind. With the only problem with saying a 50 mile per hour wind is you don't know what their averaging time is. Did they just do it on the 3-second gust? Did they do a 1 minute average, a 2 minute average? But let's just say the winds were about 50 miles per hour. And look at the middle span. You can start seeing those flex back and forth. And that's why some states have a deflection criteria. Like, I think Pennsylvania has L over 150, and AASHTO actually says if you want a deflection criteria, use a service load conditions. So in this case, that probably would have been pretty good, and you wouldn't have had that much deflections. So let's talk about how we want to distribute the wind loads through the girder system. And this is semi-covered in LRFD 4627. Now you have to remember this is more written for the final design, but if we look at the third load path, this article gives you all these different load paths. You know, if you have this, you can do that. If you have this, you can do that. Well, in the third load path, it says, hey, if you don't have a horizontal diaphragm, like AKA the concrete deck in place, and you don't have any in-plane lateral truss system, basically distribute the loads as a continuous beam. The flanges are acting as a continuous beams across the substructure supports. And that if you have cross frames in it, you can distribute that to all the girders. And then they provide a nice little equation right there to develop the wind load. It's basically in two components. You have the local effect, which is that WLB squared over 10. That's the flanges bending in between the cross frames. And then the second component, the WL squared over 8NB, is the global bending. I'm bending between end bend 1 and pier 2, and pier 2 to pier 3. It's just like your vertical loads. And you can add those two together. And then to develop the lateral stresses, you would say, okay, well, I'm going to divide my wind loads between my top flange and my bottom flange, divide by the section modulus of the top flange, and that's my lateral bending stress. And so we had all these pressure coefficients, and we said to ourselves, well, you know what? Why don't we run some models and just look at the distribution of these lateral loads? Because we know the loads for these tests, and we know the pressure coefficients for each girder. So we came up with some finite element models, and here's just a screenshot. The model for this case was 5 girders. The modeling technique used beam elements for the cross frames and the flanges, plate elements for the webs, and the loading was actually put on as a pressure on the plate elements of the webs. And you can see right here, this is our windward girder, so you see the largest pressure here, probably 0 pressure there, it's smaller, and it just goes according to the pressure coefficient. And so what are our results? Well, let's look at this graph right here. The x-axis is the length along the girder. This is a 2-span bridge. This axis, the y-axis, is the lateral flange deflections, and we're plotting the top flange and the bottom flange deflections for the exterior girder. And basically, you can't tell the difference between the two lines. Basically, the cross frames are holding those girders in place. There's no twisting. In the weak axis, the girders are bending about its weak axis. So on the chart over here, we have plotted all 5 girders. And what you see on the x-axis, again, is the length along the bridge, and the y-axis is the lateral moments. And you can see 2 divisions of lines. This is 5 girders for the bottom flange, and these are the 5 girders for the top flange. And you can see that they're not equally distributed. Basically, they get distributed by the relative stiffness of the flanges in the girder. And you see these little scallop areas. These vertical lines are the cross frames. And so that's that local effect of the bending between the cross frames. You get a little scallop, a little pickup of wind loads. And so that's more in line with the AASHTO equation. And so just to run through some numbers, here's an example. It's a two-span bridge, basically 129 feet by 159 feet. The web height's 4.5 feet, 5 girders, so say all the steel's up. The girder spacing's 11. So the first thing you want to do is the S over D ratio, which here is 11 over 4.5, and that's equals 2.4, so that's less than 3. So that gives you 2 bits of information. It tells you what pressure coefficient you're going to use, and it also tells you what shielding model you're going to use. So the first thing we want to do is use the equation for the pressure on the wind, and we know right here, for this particular example, KZ is 1.17. The velocity here is 130, and you see a 0.6 here. The 130 is based on final winds, the 50-year design life. We're looking at a 1-year event, 6 weeks event. So Florida specifies any construction period less than a year, use a 0.6 modifier there on your velocity. And that's your construction wind loading. And you know, when that's square, that really lowers the wind pressure. And Florida actually has 2 different criteria. It's called an active construction and an inactive construction. If the contractor leaves the site and a wind event comes, you really want to be a little higher load. So that's the 0.6 factor. If the contractor's lifting up the girders and they're doing work on the site, they're in control of the site. They can see what the weather's coming in. So we use a 20 mile per hour wind for that condition. And then finally, you have the gust factor, which is 0.85, and then the CP value, for if you looked at the chart for high-shaped girders for S over D less than 3, it's 2.2. Crunch through the numbers, you get 0.034. The wind pressure, our shielding model is going to be the projected height, so you just multiply by the projected height, and you get 0.18. Since we have cross frames in there, we're going to say that can be distributed through all 5 girders. And so if you wanted to find out the lateral flange bending stress along the entire girder, you can run a line girder analysis, develop your moment coefficients just like any AISC charts there are, and get all those coefficients. And for right here, we show that graph, and we're going to look at the mid-span of span 2, which is 0.65 FL. We see that the coefficient's about 0.03. Go through that equation, and we find a wind load due to the global effect is 61 kips. But for the windward girder, we have that wind pressure on that girder, and we want to get the wind moment due to that effect, and that's basically the WL squared over 10 because of continuous beam. So that's 3 kips. And finally, we want the whole thing for this is to get the flange lateral bending stress. And basically, we need to check the 2 criteria up here, the 1/3 rule, you know, when you add 1/3 of the bending stress to your primary vertical stress, and the summation of the 2 stresses. And so what we found out, since the girders basically deflect equally, you don't have to use the individual section modulus. You can use the weak axis of the girder modulus. So you can compute your weak axis girder section modulus with the top flange, web, and bottom flange. And if we want to get the stress for the top flange, since this is an 18-inch flange, we're looking at a wide distance of 9. So that's the section modulus with respect to the top flange on the weak section modulus of the girder. But for the local effect, we probably just want to look at the top flange by itself, and that's just I over Y here. And so we have the 61 kip foot for the global divided by the weak axis moment of the girder, the 3 kip over the section modulus, and we get 2.5. So here's the big difference. If you went through the AASHTO one and distributed it equally, you would get 8 KSI. In this particular case, it's not a big difference because I have 5 girders up there. If I had 2 girders up there, it'd be 5/3 times that amount. And what we're concerned about is usually in the positive moment region, because we're designing for composite construction, our top flanges are smaller and narrower. So we're a little concerned about the top flange, and this way of doing it over the weak axis probably estimates that lateral flange stressing a little better and gives you a lower number. And so, to summarize the two ways, you have the finite element analysis and the line girder analysis. The finite element analysis is shown in blue. The line girder is shown in orange. You can see that this is the length along the girder again. This is the flange lateral bending stress along the y-axis. And they pretty much are right on. These peaks right here are flange transitions. You have to do a little extra calculation, like the left side of the splice and the right side of the splice because of 2 section moduluses. And locally, you have to add in that local effect. So it's a little tedious, but if you just are looking at maximum positive moments, negative moments, and your flange transitions, it goes rather quickly. And the results are pretty well reasonable together. So let's go to the true and false statement. So this is the end. So just bear with me. So let's see if we answer this. True or false? Only the windward and leeward girders receive wind loads. Thank you. False. The drag coefficients are equal for all beam types. False. For Florida, since we had the steel girders and our Florida I-beams with the 4-foot top flanges, and we have box girders, those are different. The third one, wind velocities are the same for the continental USA. False, right. The main part of the continent is all constant, but once you get close to the coastlines, you got the hurricane effects, and so you got a lot more contours and a lot higher wind speeds. The drag coefficients for the completed bridge are the same for the partially constructed bridge. Not as confident in that one, but that is false. Traditionally, we have been doing that, but now with the new AASHTO coming in, you're going to see drag coefficients for the final structure, and then those are going to be different from any interim construction. So that is false. The girder spacing does not affect the wind load. False. The S over D. When you have an S over D less than 3, you get a lot of shielding. When you have an S over D greater than 3, you don't get much shielding. A lot of the individual girders pick up a lot of loads. And finally, the FDOT wind loading criteria reasonably estimates the wind pressure on each girder. I was wondering if anyone was going to brave to answer that one because it's a trick question. That is false. Okay? This method is to provide the total estimated wind force on the system. When you have S over D greater than 3 and that pressure coefficient shows you 0 for girder 2, well, that's not right. But when you add it all up, you get a reasonable estimate of the total wind. You don't want to get too much wind on the system because you'll get a lot of flange lateral bending stresses in there. And the other thing is the false work design. When you put lateral forces on those false works, A, it beefs up those members, but the temporary foundations for those false work systems get quite large and expensive. So the whole aim of this is to do a reasonable estimate on the system, not on the individual girders. And remember, when you're going through your stage construction of 2 girders up, 3 girders up, you're going to blow the wind back and forth. The wind comes left to right, right to left. So it won't really matter to which girders are up. So that's false. The last thing I want to leave you with is system is what we're talking about and not individual girders. That's all I have, and we have time for questions.
Time for questions. Just offhand, do you have any idea how your results built in terms of weight loading compare with the value for the shielding factors given by the National Building Code of Canada?
No, I don't.
You haven't looked at it up.
No.
It'll be interesting to see if they come out to about the same.
Now, did you say the Eurocode first, or the National Building? So the question was, how do these compare to which method again? Just that we did look at the Eurocode. They have another equations for S over D, little different than what we got here. Okay. Thank you very much.